So it's my pleasure to introduce our last speaker, Gang Tian of Princeton University and Beijing University. Among many other things, Tian and John Morgan wrote a book on Ricci Flow and the Poincare conjecture, which was one of several works that was very important in the verification of Perelman's work. So, Tian, thank you very much.
Thank you. It's a great pleasure to speak at this conference for celebrating of resolution for Poincare conjecture. Since we had the last two beautiful talks, so as quoting from Bill Suston, so their talks are more substantial and like French coffee. Now I'm bring you back to American coffee, so my talks will be more general and watering down. So make, as I said, so first let's make a general sentence. So one of the central problems in a differential geometry is to study how metrics with prescribed curvature interact with geometry and topology of underlying spaces. Because of this, since the curvature is involve a derivative of metrics, so we will get a lot of interesting equations. So in this talk, I will tell you a little bit of some equation involved in studying geometry, and particularly in the Ricci flow, which plays a crucial role in solving a Poincare conjecture. So as many people already did, like yesterday, and talk about the spatial dimension in mathematics. So 2 dimensions, 3 dimensions, and 4 dimensions. So I will follow the same pattern, and so I will start with dimension 2, and all the way go to dimension 4, because that's what the title of my talk suggests. But I will talk I talk about it from a different prospect, maybe more geometrical analytic, and so with a little bit emphasis on how differential equations play the role in studying geometry and topology. Okay, so let's start with the surfaces. So of course we saw many surfaces in this talk and with the beautiful pictures. So there will be no picture in this lecture. I shouldn't make a statement too fast, but basically no picture in this talk. So in curvature in the 2 dimension is only a one function. So it's determined say the function given by k. So most natural condition on the metric is to make this function constant, because constant is simplest function. So then the natural question is there a metric with a constant Gauss curvature? So on a given space, given Riemann surface. So we can approach this problem by a PDE method. So giving any metric G0, we can deform it by in a certain particular way, since I said the curvature is only a function, and since you want to make function to be constant, you just change a metric by a function. So then you already have a good chance to hit it. Okay, so if a metric has a constant Gauss curvature, then you can sorry, I have to get used to it. So if this new metric has a constant Gauss curvature, then U satisfies the following semi-linear equations. So this is you can easily get it simply by computing a Gauss curvature for both metrics. Okay, so that's first thing you can do. If I'm analyst or differential geometer, I just start with a metric. I do a change in the particular way. This particular way does not change a conformal structure of underlying space. So then you get the differential equation. So everything follows from a direct computation here. So it can be solved. And of course, I'm not going to solve it here. And so it can be solved by using an elliptic PDE method. It has been studied for a long, long time, and starting in the 60s, the 70s. And it can be solved. So conclusions can be solved. And also, it can be solved by using a curvature flow method, which was started later by Richard Hamilton and Benchel and many others. So the outcome of this whole thing is a following theorem. So giving any two-dimensional manifold space M and a conformal class. Conformal class simply means you start a metric and you only change a metric in the way I just said. Okay, just said this one. I said it does not change angles, and so then there is a unique normalized after normalization with a constant Gauss curvature in a given conformal class. So then there is a very classical theorem in the remaining in the differential geometry, or in this case on the surfaces, called uniformization theorem, which says you can immediately derive, say since the curvature is constant, then its universal covering is given by this, and gamma here is simply a fundamental group. Okay. So as Simon said yesterday, I guess as Simon said yesterday, you can also use the Riemann mapping theorem to prove these conclusions. But here there's a little difference between using a Riemann mapping theorem and this PDE method. So this PDE method here is at a priori, you don't know what the space is. And what you started, you just study abstract space surface, and you set up differential equations, you try to solve it. And if you're lucky, you can solve it, you will get this. Okay? So you conclude it. You conclude the surface is completely determined by fundamental group up to certain ambiguities. Okay, so once you go to high dimensions, and the curvature become more complicated. As said yesterday, curvature has more components, and one of a particular part of a curvature is called Ricci curvature. So that gives you an Einstein equation. So Einstein equation original, of course, is involve hyperbolic metrics, Lorentz metrics. But here, let's just in geometry, so far we only concerned about the static case. And so let's look at the Riemannian metric G, and this is Ricci curvature. If this equation is satisfied, then we call this Einstein metric. Okay, and it has Ricci curvature has certain geometrical meaning. Namely, it measures how the volume form deviates from Euclidean ones. Okay, so in a dimension 2, as we know, it's an Einstein metric is simply a metric with a constant Gauss curvature. Okay, so in terms of local coordinates, you can, of course, you have a choice of choosing coordinates. So that's you can write Ricci curvature as like Laplacian of metric and plus low order terms. That's terms only involve first derivative of metrics. So this tells you this equation is nonlinear. That's actually you already saw it in the 2 dimensions nonlinear, but this is in the high dimensions make things more complicated. Okay, so now let's assume M is a compact 3 manifold. I only say a few words since we already heard a lot about this Perelman's proof of geometrization conjecture. So I just as a passing, so I say a few words. So in the 3 dimensions, what still holds is if M admits Einstein metric, that is this, as I said before, then the M is still of this particular form. So this is same as two-dimensional case, same as two-dimensional case. So then you can ask a question, like what we did in dimension 2 is does M admit the Einstein metric? As we all know now, in general, this is not true. So the Solston's generalization conjecture basically says any three manifold can be decomposed in a lateral way into pieces which either have an Einstein matrix or have some special structures called graph manifolds, and the Poincare conjecture is a case of it's a special case of this. Okay, so Perelman has solved this conjecture by using Hamilton's Ricci flow. Okay. So here is a Ricci flow since I don't know if I ever. So anyway, so this Ricci flow. So this is almost like it's essentially a parabolic flow. So you can have a local existence, which is due to Hamilton himself and the torque. Okay. And also Hamilton established a rich analytical theory for this flow, and which plays a very important role, crucial role in the resolution of Poincare conjecture. And also there's one more point which since my talk will emphasize as we will see the singularity formation of things. So I should say also somehow more on the analytical part. And so I should add here there is a particular point in Richard Hamilton's work, and which plays a crucial role in the dimension 3, that is curvature evolution. In the dimension 3, because of curvature evolution, because it's a pinching estimate, which gave a crucial tool to analyze the singularities, and which is missing in the high dimensions. Okay. And so as we know, if a Ricci flow has a global solution, or at least as Richard Hamilton proved it, maybe possibly after appropriate scalings, and suppose this global solution converges to a smooth metric G0, G infinity, as t goes to infinity. Okay, the global solution here simply means t exists. This solution exists for all the time. So then it's this limit metric G infinity has to be an Einstein metric. So the universal covering of M is standard, as I said before. This is true only true in dimension 3. So as analytically, this geometrization becomes a problem. At least it reduces the problem trying to find the global solution, and with this asymptotic behavior. But life is complicated, and that makes things more interesting. So because the Einstein equation is nonlinear, it's highly nonlinear, and it may develop singularities. So the key things in the Perelman's work is he gave a complete understanding of topology of singularity formation in dimension 3. So this basically there are two, and there are many, there are many things he did, including things Bruce and Besson talked about these collapsing things. But also there are two main technical advances he made. So one is the injectivity radius estimate, so-called non-collapsing. So at any finite time, the Ricci flow the metric along the Ricci flow does not collapse. Okay? So you have a certain injectivity radius bound. The other one is a curvature estimate, which tells you, so when the curvature is big, the space becomes more curved, and if a space is if a flow comes to close to singularities, the curvature is supposed to be very big because space will be very, very curved. So this curvature estimate also plays a very crucial role in paramount approach. Okay, so as Bruce mentioned in the morning, so in fact this question here is still not quite solved, even though we understand completely the topological aspect of Ricci flow. Okay, so that's about dimension 2 and 3. So next I will go to dimension 4, as I said. So I want to tell you some of these things and I can do, and or some other people can do, and possibly probably raise some questions we can do in the future. Of course, to study 4-dimensional manifolds, there are still a lot of unknowns. So my next part of a talk will focus on, in some sense, focus on these two parts about curvature estimate, what we know, and injective radius, and what we can derive from that. Now, before that, I give you some motivation why we want to do it. So let me focus on four manifolds. So the situation is very different in dimension 4, as we already saw it yesterday, because there are more curvature components in the dimension 4 and higher. Okay, then say, okay, why don't you go to higher dimension? Because higher dimension, the Einstein equation, of course, become more complicated, but it's not clear what the topological and geometric consequences are, and so people may now study the higher dimension, Einstein metrics, just of a certain type, so-called self-dual type. Okay? So that's appeared in string theory and things like that. So we can still ask a general question: what are canonical metrics on the 4 manifolds? So to talk about that, let me recall some very simple fact. So in dimension 4, the special structure is the self-dual structure. This particular structure called self-dual structure. This corresponds to a decomposition of this Lie algebra. This is simply a space of it's simply a Lie algebra of 4x4 schizommetric matrices. So similarly, this is 3x3 schizommetric matrices. So there's a natural decomposition. And decomposition can be given more explicitly, so by so-called Hauge operator. So of course, Hauge operator can be defined for any vector space with the inner product. So let's here just giving in this particular case, this is giving explicitly. So other part is just symmetric to this. Okay, you make it the square of this to be identity. So now giving a Riemannian 4 manifold, so metric G is simply give you a family of inner product on the tangent spaces. So then this can extend to operate on by a wedge 2 of a tangent bundle. And because square of this is identity, you can decompose this into according to this corresponding to this decomposition, you get to be a plus part of a minus part of by tangents. Okay, so the self-dual structure, I say, was already used in the many previous works, including so let's just mention one, which we already mentioned before. It's for example, constructing Donaldson invariants for 4 manifolds in the early 80s, and subsequently in the Seiberg-Witten invariants. So many nice theorems were proved. So similarly, the self-dual structure needs an interesting canonical metric structure in dimension 4. So in order to talk about that, let's see this well-known fact about the curvature decomposition of metric G in dimension 4. Because of the previous decomposition, you can and also because the curvature is simply a symmetrical operator on the bitangents. So then you can write the curvature in this 6x6 matrix, and there are 4 blocks. Each one is 3x3, And so the meaning of this is the W is a Weyl tensor, which and it has two parts, plus and minus part. And the geometry meaning of Weyl tensor is to measure conformality of metric. So Z is essentially a traceless part of Ricci curvature. So and S is a scalar curvature. Okay. So there are two types of canonical metrics on the four manifold, and so they are in some sense all self-dual type. And one is the G is Einstein, namely Z is 0. So this previous matrix is diagonal. And also you can say G is anti-self-dual. That means W plus is 0. And you add one more normalization, namely make scalar curvature to be constant. And it turns out this is also well-defined elliptic system. And those two have overlaps. For example, hyperkähler metrics. They are both Einstein and and anti-self-dual, as Simon mentioned yesterday. So actually one can do a little bit better in in the case of Kähler geometry, we are like now it's a very active field to study so-called Kähler metrics with constant scalar curvature. So in some sense, this so-called extremal metrics, it falls into second class. In this case, the W plus is not necessarily 0, but it can be written as a function of a standard function of a scalar curvature. Okay, so it's a should behave rather like anti-self-dual metrics. So I said I give you some motivation. So first is the existence of such a canonical metric still imposes a strong topological constraint and the underlying four manifolds. Let's make it more interesting, at least in some sense, more interest to study. In the high dimension, it's not clear. And we have not known any of such things. So for example, if play around these curvature properties, decompositions, you can prove if M is homotopic to force field and meets anti-self-dual metric, then it's diffeomorphic force field. The things is you have this metric, you can prove this is conformally flat. Okay, and we can also, as Simon mentioned yesterday, there's this hitching soft inequality, and for Einstein, for any four manifolds which admit Einstein metrics, and this follows from Gauss-Blake theorem and index theorem for signatures. Okay. And you can even, Hitching even did more. He checked the case for equalities. Okay, for equality. So you have these topological constraints. So for example, and this is because of this, you can check for this connect sum of CP2 with CP2 bar. CP2 bar means you change the orientation of a complex projective space. And do not have any Einstein metrics if k is bigger than 9. And by now we know it's for k less equal to 8. They do have Einstein metrics. And we can also show if M is a spin-4 manifold, if it's homomorphic to a connect sum of Einstein 4 manifolds, that means this piece, and each piece has Einstein metrics. Then you can have this S. You can check S11's conjecture. Okay, so then the signature and Beatty number have such a inequality, and there is also improved version of this Hitching soft inequality by Claude Lebrun. He proved if a four manifold has a long vanishing Seiberg-Witten invariant, so that's actual condition, and has an Einstein metric. So then you can increase you can drop these two on this side in the previous inequality. And this actually extends a Muir-Yao inequality for complex surfaces. So I just show a few examples of this constraint imposed by canonical metrics in the dimension 4. There are more results of this type, and because of time, I will not go into list each of them. So So of course, there are also many existing theorems, which I just mentioned. So make it say we are not completely, and we do know a lot of Einstein metrics. First, for complex, for Kähler surface case, this is completely solved, and also for full manifold, the Tops proved a wonderful theorem, which says if you make a sufficient copy of a connexon with, if we make connexon with sufficiently many copies of CP2, that also admits self-dual metrics. And there are also construction by using twist spaces. Okay. So also analytically, there's this gluing method to construct many examples of Einstein full manifolds, like by people like Michael Anderson and Bequire and Franco Parquet, and actually also my student Bomer, and many others. So there are a lot of examples. So still we want to understand this just give you an example. We still want to understand say how general we can produce the Einstein metrics. So Ricci flow, Hamilton Ricci flow is still it seems to be a only general method at the moment to offer deforming a given metric towards an Einstein one. So this at least provide you a mean. Say if I start with any metric, I want to evolve this to a good one, and following natural evolution process, because Ricci flow is like heat equation is a natural evolution process, even though we don't really understand even in dimension 3 or dimension 2, and when the flow has a lot of consequences, but this natural evolution does not give you all the details in the course. Okay, so of course we also expect the Ricci flow has a global solution with surgery as in a suitable sense. So of course this is not known yet. So that's the solution either become extinct in finite time or after many surgeries. So we basically expect the kind of things you had in dimension 2 and 3, and particularly dimension 3, because you do expect singularities. So this is indeed the case if an initial metric satisfies some actual conditions, such as a positive curvature operator. If you assume initial metric has a positive curvature operator, Hamilton proved this flow exists and become he can solve the flow, Ricci flow up to a certain point, and then near that point, if you blow it up, you get you converge to standard metric. Okay, so you can also do a more interesting case is a positive isotropic curvature. That's a weaker curvature condition, and Hamilton and some other people proved after certain surgery you can construct a solution with surgeries and to give a classification of a manifold with isotropic positive curvature. Okay, so let me show you one more examples, which is in a sense more recent. In a different, little bit different spirit. So if I start with, if I assume the full manifold is complex surface, if the initial metric is Kählerian, I don't impose a condition on the curvature, but I impose condition I restrict conditions to certain kind of metrics. So then it turns out, in this case, you can understand the singularities. You can understand the flow, how flow develops singularities. For example, this case, any finite time singularity is caused by a presence of holomorphic fields of a self-intersection number -1, 0, or 1. There are 3 kinds of them. Okay, that's actually only 3 kinds of them. As I said, this is rather general talk. I don't want to go into how to describe that, but this is basically. So you can ask, for example, since the existence of an embedded field with self-intersection number -1 are rather stable, maybe you can ask whether more topological question whether or more analytic question in general case, does the embedded tooth field of self-intersection number -1 cause a finite time singularity? Okay. So certainly this is true if you impose a condition on the initial matrix. And moreover, so you can say a little bit more, namely, if a Ricci flow, I guess I should drop this mail. Okay, if a Ricci flow collapses M to a point at finite time, namely in the finite extinct, so then I'm still talking about the Kähler case. So then M is a Del-Peso surface. It's like CP2 or S2 cross S2 or this elliptic type. And if a finite time singularity is caused by a holomorphic field of a self-intersection number 0, so this is caused by self-intersection number 1, actually, or more positive. So then the Ricci flow collapses to a Riemann surface at finite time. So consequently, the M is a ruled surface. And after finite time, you expect your flow descends to a flow on the Riemann surfaces and continue there. Okay? So then you reduce two-dimensional case. And the one more case is otherwise, this, if you only have a holomorphic field of self-intersection -1, then this flow continues on the blow down of M. So you just simply contract down that embedded sphere of self-intersection -1 and continue the flow. And after, so if you don't have a sphere of this type, then you actually have a global solution. Actually, you can have a global solution all the time to infinity. Okay? But in general, if you have those bad spheres, you do a surgery on them, and then you continue the flow. After finite time, you end up with either you know what the space is, or you end up with a global solution. So moreover, as t tends to infinity, after suitable normalization, there is a global solution. That means after certain surgeries, converge to either a Kähler-Einstein metric or a collapse to a canonical metric induced by myself and Zhang Song on a punctured Riemann surface with prescribed behavior around those punctures. Okay? So those metric, I don't want to write down the equation, not Kähler-Einstein metric. It's not a hyperbolic metric on the Riemann surface, but they behave rather, in some sense, very similar to a hyperbolic metric on Riemann surfaces. So this, in the second case, for example, it does happen. It's some sense correspond to a Perelman's case of this graph manifolds. So that means the four manifold has certain structures, certain structure ruled by tori this time. Okay, so for example, I give you point out that there's an interesting phenomenon here. So for example, if I start with an elliptic surface, and let's say M is non-special, namely you have to get rid of certain two examples. Okay, otherwise you can analyze that, but the geometry at infinity is slightly different. So then let pi m prime is be another elliptic surface obtained by doing logarithmic transformations along the two smooth fibers of pi with co-prime multiplicities. Okay? So then we know by Friedman's theorem, these two manifolds are homomorphic. Okay? They are homomorphic, but not diffeomorphic by Donaldson theory. That was actually one of surprises in the early 80s. That the Donaldson theory can actually give you can be used to prove they are homomorphic manifolds with different differentiable structures. So, however, if you look at the flow, look at the Ricci flow here, they deform any Kähler metric. Since both are elliptic surfaces, they deform any Kähler metric on M and respectively M prime to a canonical metric G and G prime, okay, on S2. And both G and G prime satisfy same equation on S2. And the only difference is G prime has two actual singularities. And these two actual singularities are not too complicated. They are just conic singularities. They're caused by with the same multiplicity as those as those multiplicities, you perform the logarithmic transformations. It's certainly this is true for all the Kähler surfaces. Since you can perform this logarithmic transformation along the many pairs of fibers. Okay, so you can get a lot of different differentiable structure, many different differentiable structure. But in the end, the metric is still the canonical limit. They still have certain common things. So of course this is just for this Kähler case. So whether this is sum of like this can be said in a real case, I don't have a clear thing to say, but I certainly believe there must be some connections. Okay, so a lot of these differentiable four manifolds, which are not of these four manifolds which with different differentiable structures, and came from construction along the tori, which has the trivial normal bundles and homologous to 0. So this in this particular case is a pair of fibers. So I wonder whether what those logarithmic transformation in general case cause the problem singularity formation for Ricci flow. Okay. So as I said, it remains to understand the singularity formation of Ricci flow in dimension 4 in general case. Of course, it's an interesting question. What I said before is for Kähler surfaces, we understood them completely, how these finite time singularity in 4 dimensions. So of course, I expect those singularity formation are rather stable. Then in a sense, if you perturb your initial data into like real in the general cases, I hope those singularity formation, or these at least finite time singularity still persist, and so it seems to be a doable things, at least something to be checkable. Okay. So to understand the finite time singularity and those singularity form at infinity, and are still a crucial question and largely open problems for Ricci flow in dimension 4. But we know more about the second case, namely singularity formed at time infinity. The reason we know more because what I mean always mean in general case now is in a 4 dimension there is no such a curvature, at least not known, the curvature pinching estimate of Hamilton like correspond to this curvature pinching estimate dimension 3. So we a priori we don't know any possible curvature constraints after when you scale up the singularity finite time. Okay, so at least there is a case even in dimension 4. There's some new things, as we know, as I said before, and as people said yesterday, is in dimension 4 the curvature is weaker. There are more components in the curvature. So Ricci curvature does not determine a curvature. So because of this, even Einstein metrics are more flexible than it's less rigid than as we know in dimension 2 and 3. So first things we want to know is to understand the singularities, or all the possible singularity for Einstein for Einstein metric on 4 spaces. Okay? So this is something I did with Jeff Chigger, and Jeff Chigger and I have a few years ago have established 2 such a estimate for what I mean is the curvature estimate and the injected radius estimate. So let me tell you a bit of these 2 estimates. So first estimate is a curvature estimate, which is the following. So it turns out you don't expect bound curvature everywhere because that's not possible. And but there is a much checkable condition in order to keep curvature bounded for Einstein metrics. So namely, there is a uniform constant such that if you take any Einstein metric of a dimension of dimension 4, and on this geodesic ball here, and this is simply normalization, then we proved this smallness of L2 norm implies a curvature bound on a smaller ball. So you only need to check L2 norm to be small or not. Okay. Of course, if a curvature blows up, if a curvature bounded, this is clearly true because the volume of this could be small. And also, this is scanning invariant. This is a scanning invariant here. And also, by Gauss-Bonnet theorem, the total L2 norm of curvature is bounded by Euler number. Okay. This in some sense is a standard regularity theorem for geometric equations. There's a couple of differences here. There's one fundamental difference here is for example, for harmonic maps, minimum surface, and so on. With a curvature bound, you immediately imply your underlying space has a simple topology. But here, we know the topology of this space topology geodesic ball is simpler, is basically of a quotient type. Okay, so it's a simpler, but not completely like a Euclidean ball, not necessarily Euclidean ball. It could be still collapsed. So volume could be still small. Okay. So, and as I said, because L2 norm of curvature is bounded, is same as is simply a multiple of Euler number if Mg is a compact Einstein full manifold. So it follows that for any R positive, there are only finite many points, and outside the finite many points, the curvature are bounded. So that is for this Einstein full manifold. Once the Euler number bounded, you can only at most develop singularity at finite many times, and the number of points, at finite number of points, and the number of points is uniformly bounded by some topological numbers. Okay. So this I just showed you one consequence. So once this is curvature bounded, then I know this outside the finite many point, the metric and the space are controlled, and controlled up to some group action, and this group action is it's not so complicated in dimension 4. Okay, it's essentially Euclidean nilpotent group action. So this actually we expect this curvature estimate is also true for global solution of Ricci flow at time infinity, because this is based on a speculation. It's based on the work of what I did with Hong and for Yang-Mills flows. Okay. But this is still open, how to do it, same thing on the Ricci flow. There are some partial results by my former students for Ricci flow and certain assumption on the Ricci curvature. But in general, it's still open. See? And so my second estimate is injected radius. So namely, of course, in general, you expect a collapsing, but if a Ricci curvature is not vanishing, it's not zero, then there's no collapsing. So you can bound the injected radius at most of points. Okay. So of course you cannot for positive case you can bound everywhere. For negative case, so that's essence of our theorem is you certainly cannot expect bound everywhere because they might have a cusp at infinity. Even 2 dimension, you have a cusp at infinity, but you can bound most of part. Okay, most of part, and all other parts are for degenerate parts are rather supposed to be simpler because they are collapsed to lower dimensions. So without maybe I say a little bit more about this curvature possible singularities, and give you some idea what is known, what is still not known. So for this, let me, without loss of generality, let's assume XD is a Nen space. So it's a limit space of a sequence of Einstein for manifolds. Just try to make it simpler, okay? And to describe. So then this limit is already exists because of this, always exists in the Gromov-Hausdorff topology. So then the problem to analyze possible singularities for Einstein equations in dimension 4 is reduced to understand the regularity of these things. Okay? So there are two cases. One is non-collapsing case, namely X has dimension 4. Okay, that's same dimension. The limit has the same dimension as a initial as a space you start with, and the collapsing case. So that's why I say I have one picture. So that's the only picture. so non-collapsing case was actually well understood. Is for example, at any finite distance, you can only see a quotient singularities. Okay, so it's any finite time, the singularity only caused by finite group quotient. So this is a typical example. You take this hypersurface in C3. This has a Calabi-Yau metric. And as if when epsilon is not 0, this is smooth. As epsilon goes to 0, you get this space. It's a cone. Okay? And it turns out at any finite distance in non-collapsing case, that's only singularity you see in dimension 4. That's not bad. In dimension higher, it's more complicated than that. Okay? So, and there's other group of singularities, namely complete Einstein for manifold with finite volume. And so those are what I mean singularity at the infinity. For Riemann surface case, that's the only singularity you see for hyperbolic Riemann surfaces. Okay, so that's still called their cusps. So we still need to classify all the possible cusps. So in the Kähler case, and those models, all of these cusps has explicitly given by in my previous work with Yang. Okay, in the 80s. So Kähler case, they are known, but in a non-Kähler case, we still need to analyze them. It's possible to analyze them because this is cusps. At infinity is actually collapse. So they actually should reduce the low dimensions. But I think it's doable, but still, there are many. It's not done yet. Okay. So then second case is a collapsed case, which is more complicated. So more complicated because this is more. It's not this cusp case because then that case is more like curvature bounded case. So this is why I talk about here is more complicated is because like Ricci flat case. It's like finite distance. Okay. So there are examples. For example, this Gross-Wilson this provide this example for K3. So that's also studied in the mirror symmetry. So it's called large complex limit things. So in the last couple of years, my former student Aaron Leber and I did some study on this and made some progress. So basically we try to see how still we can try to do analysis even the space drops. So for example, to derive a limiting equation, we want to still see some equation in the limit, okay, in the general case. And so there are a couple of things, because time maybe I skip some of that. So for example, using a Kähler the result and Kähler and myself, one can prove outside finite many points, so away from finite many points, the x is the limit, the collapsing case is actually remaining orbifold. This is only true for dimension 4 and less. Okay. In high,
what is dimension 3?
X is dimension 3 and down. Yeah. And so X is this time if a dimension is 4, and this is orbifold. But of course, X has smaller dimension than 4. So we still need to understand the structure of this X near the PI and classify all of these. Okay. And So I mean, the simpler case, you assume this limit, say, Ricci flat, and has no PI, say, namely no concentration of curvatures. So then the X is actually a flat orbifold. And moreover, you can, that's probably already follows from previous statement. Moreover, this Mi before the limit is just orbifold bundle with nilpotent manifold as fibers. Okay. So anyway, so this is so the key issue now is to analyze the structure of this space near this PI. So this has two parts. One is analyze structure of this limit space near PI, and also analyze the structure of Mi near the PI, and how this collapse to that. So to at least one thing you can, by following some standard analysis, is you blow up, right? Once you see a singularity, try to scale up and try to see more clearly. And so once you do that process, carry that process, then we are led to studying a complete Ricci flat metric with these conditions. And my curvature estimate with Jeff actually implies for this space the curvature decay at least quadratically. Okay, so there are a lot of things to known for this space. So, but in general, still it's quite a bit tricky. So, but what about Calabi-Yau case? So for Calabi-Yau case, so if that means I look at these complete Ricci flat spaces with a finite curvature, total curvature, and assume it's Kähler. So there are models. For example, by Hitchin and Kranhammer, you have this M might be a quotient of CP2, and by finite group, then you take a resolution. So this is called ALE spaces. And you might have like a top-lot metric on the C2, and also uncertain quotient of C2, resolution of a quotient of C2. So this, according to physicists, they call ALF space because asymptotic is not flat. Okay, so in the late 80s, Yau and I construct this so-called ALH space. That's a new name. Okay, so this metric has the properties asymptotic is like cylinder. It's like a S3 cross T3 cross R. Okay, so very recently, my student Han and current student Han has constructed a very large class of complete Calabi-Yau metrics, including some earlier ones constructed by physicists. Okay, so these things certainly include some of these. Also include so-called ALG, ALH spaces, and they actually not of them. I mean, of course, even not of them is a finite list. Okay, once you control the order number. So the question are there other ones? Actually, I expect the Han has produced all of them. So at least those give you all the singular models for this collapsed singularity of Einstein you can find in at those how do I say at those curvature block point. Okay, but this is a Kähler case. This is still a Kähler case. Okay. So if above is expectation holds, then in case of Kähler-Einstein, there are basically only two types of singularities for those PI. One type arises from minimum surfaces. Well, I'm talking about collapsing case of a finite quotient by C2, like ALE space, ALF space, or another arises from a rational elliptic surface with one fiber removed. So one fiber could be singular fiber, could be smooth fiber. If you remove the smooth fiber, that's what I did with Yau. Okay, and what others are due to Han. Okay, so of course I also ask for real cases. So this provide this give you very give you some hopefully give you some idea why we come to study these complete Ricci manifolds, because they provide the local models for singularities in a collapsing case. So maybe finally, let me just say, in my talk, I focused on the Einstein case, and I said there are also another class of canonical metrics, so-called anti-safety metrics. Because for anti-Safety metrics, we don't a priori control Ricci curvature, so we cannot use the so-called Bishop-Gromov volume comparison theorem, so which played the role in studying Einstein equations in dimension 4. Nevertheless, last year I was able to extend this curvature estimate to a case of anti-Safety metrics with normalizations. And non-collapse case of this was already proved by myself and Jeff Wiatkowski many years ago. Okay, so based on this curvature estimate, and one is made possible to carry out similar things as I just described for anti-Safety metrics, and conceivably, some of these analyses are easier in the anti-Safety cases because when you scale up, it's not like Ricci Flow. It's already also has anti-Safety structure. So analysis might be a certain analysis might be a certain way be different, but might be simpler. So anyway, so maybe this is general question. So we have this wonderful theorem of tops for deforming to construct a lot of anti-Safety metrics. But in general, I always wonder whether there is a flow method for anti-Safety metrics, which is somehow in the opposite to TOPS construction. So we have Ricci flow for Einstein metrics. I don't know about for anti-Safety case. And thank you.
Thank you very much. Thanks again, Tian.
Sure.
Thank you very much.